So welcome to the real first sessions of the machine learning course. And every lecture which we're going to have is going to be recorded. The README file on the GitHub address is the one which contains the basic information and with links to material. I have actually created a Slack channel, and there is an invite which expires in 30 days. And what you can do then is to log into Slack if you want to, and just use that one, just register your username. And I will use Slack, although University of Oslo doesn't support Slack, because it's presumably violating some of the data privacy regulations of the European Union. But I find Slack an extremely useful tool to use for communication about projects. And in case you guys want to team up in groups, this is a very good way to get started with. So I put it in the Slack channel, in the chat here. You can get the Slack link if you, this is an invite which lasts something like 30 days. So last week, what we did was more to have a presentation of each other so we could get a kind of view of what kind of background people have and what their interests are. And based on the feedback, I actually only have 7 people who answered about examination forms and so on. So before we conclude on that, I would like to have, or to ask you guys to call, for those of you who have not answered, to actually give some input to the questionnaire which we had about examinations forms and topics, etc., etc. So the topic today, since some of you expressed the need for revisiting the basics of feed-forward neural networks and the first entry point for deep learning methods, the kind of idea now is actually to use today to remind you all about the basics of a neural network. And then we are going to link this to the coding, which we are going to develop, and then try gradually to link this up with the first project. So let me quickly switch to the Jupyter Notebook. Right after the lecture, I'm going to post the handwritten notes and also the video of these lectures. And you can also dive into my old lecture notes, and these will be updated with more information. But into this week 2 here, or the second week, which we are in now, this is roughly what I wanted to say, to talk about today. So a review of deep learning, some of the basics of neural networks, and we are going to essentially do this through a whiteboard, and prosit, by the way. And then we are going to discuss possible paths for projects here. So although this is as we discussed last time, is something which is set up as a self-study course, I thought we could have a series of lectures in the beginning, and then people can, depending on their interests and needs, if they don't find this of interest, they can easily just keep working on projects which are more related to their master thesis or PhD thesis, which we may not have time to cover because there are many topics which we can actually cover. So if you look at the this image which we have in the beginning here, so the topics which we will put a lot of emphasis on will be more on the axis above here, where we have unsupervised learning and supervised learning. So we are going to look at the traditional deep learning methods for supervised learning, which would be a neural network, convolutional neural networks, and recurrent neural networks. But then we will dive into unsupervised learning, and in particular with an eye on dimensionality reduction. And this is something which is of great interest for a lot of physics modeling, especially if you're dealing with the solution of partial differential equations or differential equations. And here we will talk about autoencoders and generalized adversarial networks, which are 2 of the more popular unsupervised methods, and which are strongly linked with dimensionality reduction here. Okay, so there's somebody who, so the there's a question about the questionnaire. So I sent actually the questionnaire via Canvas. So all of you should have gotten an email via Canvas. And if you haven't linked your Canvas account with your UIO email, okay. So I'm going to check this actually. There's a question on why somebody's not on Canvas. Because I use Canvas to send out the regular weekly mails. And because that's where I have access to your email addresses. But I could,
sorry.
Yeah, go ahead. Go ahead.
Hello. It says that I'm connected to Canvas, but I didn't get any like message. And when I go into Canvas, I'm not seeing any messages at all.
Okay. Same for me.
Okay, so I'm gonna check this, why you guys are not getting any message via Canvas, because I get a list of all of you, and I thought that automatically did send an email to everybody. But if you look into the chat here, one of you has actually put the link to the questionnaire there. So I'm going to check why you guys didn't get an email via Canvas, because that's how I can access your emails. So the study administration does never distribute emails except for the official UIO emails. But I will check. I'll look into that one. Thanks for letting me know. That's a good thing. Okay, but you have the link to the questionnaire in the chat here. So feel free to use that one. And if you wish to use Slack as a communication channel, feel free to use it. I mean, it's a channel which I like to use, but it's not something which we advertise because it conflicts with the Data Protection Acts of the European Union. Okay, so that was about some practicalities. And if you have other questions about practicalities, please let me know. So we will mainly, as I said, we will mainly stay with unsupervised learning and also supervised learning. If we get time and if there is an interest, we could say something about reinforcement learning. But we will keep an eye on topics like dimensionality reduction, which is a very important topic when we are dealing with scientific problems in the physical sciences. But let's go back to the Jupyter Notebook for this week, or the slides. So what I would like to propose is a kind of path now where we cover in lectures, and this may keep us busy till we have the Easter holiday. So we would have feed-forward neural networks. And one possible project and possible path for project number 1 is to actually develop a code based on what you did for neural networks, to dive into either writing a code for convolutional neural networks, which are of great interest for imaging, or alternatively to look at recurrent neural networks. And based on these methods, we are also going to propose a set of problems or data sets which we can study. These data sets will be based on solutions of differential equations, where we use a method like a Runge-Kutta to fourth order to generate the data. And then we feed that one into a deep learning method in order to train a network and use the solutions from a Runge-Kutta solver for ordinary differential equations, and use these as data to train a model for our network. And then when we are done with these methods, the kind of idea then is to cover autoencoders and GANs. So these are the kind of this is the kind of topics which I thought of proposing, which clearly can define a very explicit path which matches many of the answers which I got from the questionnaire which we posted online last week. And so for those of you who didn't have the possibility to do so, I mean, please send me input, because then we can tailor the kind of data sets which we look at in the first part of this course here. Then, depending on how far we get, and also obviously on your interests, one possible path is actually to continue along these lines and look at other data sets. So the first data set which I'm proposing is a simple set of coupled differential equations, which are the so-called Lorentz attractor differential equations, which is a popular system for studying chaotic motion, by the way. And then I thought we could move into, for the second part here, when we have established what we are interested in, the machinery, then we can look at data which would be much more specific to your thesis work. So this could be, for instance, the solution of differential equations in fluid mechanics, like the Navier-Stokes equations. And I also know that many of you are interested in quantum mechanical problems. And that's also another possibility. And then clearly there are many other options. So if we develop a code for convolutional neural networks, like last year, we had a group of 6 people from high energy physics, which looked at the Higgs challenge, which is a very interesting case. And you can actually enter competitions and see if you can improve the data analysis from CERN with your own convolutional neural network or other machine learning methods. So I would say that the first part here now is going to focus a little bit more on deep learning methods and what we call physics-informed machine learning. And one of the examples which we could look at in the second part, that means when we are done with the first project, would be something which could go into fluid mechanical problems, quantum mechanical problems, or other types of problems. Alternatively, we can use what we have developed to move into Bayesian machine learning, which is also a very active field of research. So these are the kind of paths which I would like to propose. So feel free, when you look at the questionnaire, you can go back to the questionnaire, you can re-edit your answers. Or for those of you who hadn't had the time to answer the questionnaire, just take a look at it and try to think of what kind of paths would be ideal for you. And if there is no match, this happened last year. We had another group of students who wanted to study reinforcement learning, and they actually went on their own, and we just set up a set of literature, a set of texts which they could read and then work on problems. So I was thinking then of doing this, as you can see here, and you have the old lecture notes from physics SDK 4155, but I wanted to repeat many of the things which we have in connection with deep learning and neural networks. There's a reason for this. And one of the reasons is that when you wrote, for those of you who followed physics SDK 4155, when we wrote a code for neural networks, we didn't pay so much attention to topics like parallelization, efficient coding, but also on topics like automatic differentiation. So automatic differentiation is, in its reverse mode, is the same as the famous back propagation algorithm, which is used in neural networks. And there is a very popular library, which is called JAX, J-A-X, which in a way is an update of AutoGrad, which calculates derivatives to numerical precision without using symbolic manipulations, but it's actually a repeated application of the chain rule. So one of the things I want to do today is to focus a little bit more on the mathematics of neural networks so that we remind ourselves how the neural network is set up. And then the kind of idea next week is to go through the codes which we can use for solving problems with standard feed-forward neural networks. I know that many of you felt a little bit rusty about the deep learning methods and some of the basic ingredients. So this is a way for you to repeat what you have seen before, whether this was last semester or 1 or 2 or 3 years ago. So this is roughly the kind of, path which I would like to suggest in the next few weeks. For those of you who also want to read a little bit more, both on topics like kernel regression and Bayesian statistics, or if you want to look more at physics-informed machine learning, there is a, if you click on this one, you will get to actually to a suite of codes. Similarly, there is a numerical project here on physics-based deep learning. And there is also an article here, which actually accompanies this article here, describes the codes, which you will find in the library, which you will find in this link when you click on this link here. So if you click on this link, that will send you to what is called physics-informed neural networks. And this is one of the groups who actually has made public all their codes. And that can be something which can be of interest for many of you. So any questions to the kind of approach which we are going to take in the next few weeks? So there was an expressed wish from many of you that instead of having this as a self-study course, we could have lectures in the beginning, at least till we come to the Easter break and we have been able to work a little bit more on deep learning methods. So any questions, inputs, let me know. You can put them in the chat or you can just unmute yourself if you prefer. Okay, there were no objections to this suggestion here. And if you go back to the README file, you will see a kind of tentative schedule. This is very tentative and it depends on how far we get each week. And I will also try to guide you through, like next week, we are going to look at codes for the feed-forward neural networks, which include many of the basic elements which we have discussed earlier, like gradient descent methods, how to find the optimal parameters, etc., etc. But if you don't mind, I'm going to switch to the whiteboard, if that's okay with everybody. So let me just do that. So what I would like to do now is actually to go through some of the basics of neural networks. And then when we meet again next week, we can start looking more at codes and also how to use a library like AutoGrad or JAX, which is a pretty new standard. So let's quickly remind ourselves of the basics of neural networks. And when I say neural networks now, I'm thinking of a feed-forward neural network, or what people call a multi-perceptron model. So let's just, in drawings now, try to explain what we are going to do. So we are going to have, essentially, there are going to be two main elements. One is the architecture. So I have to learn to spell here properly, guys. Architecture, which essentially defines the model. So when we think of the architecture of a neural network, we need to specify the number of hidden layers, and then in each hidden layer, we would need to specify the number of nodes or neurons or units, as many people also call them. So I'm just going to write like this, and I'm going to interchangeably use either nodes or neurons or units. Then the other thing which we need to think of is something which is called an activation function. And I'm coming back to what this is. So this will be some of the basic parts of the setup of a model for a neural network. So these are the parameters which actually define our model in the same way as when you are fitting some data sets to a given polynomial, then that given polynomial, the order of the polynomial, defines your model. So when you're setting up a neural network, then the model is defined by the number of hidden layers, number of nodes, number of neurons, activation functions. Then we have the next part, which we now can define in terms of a cost function or loss function, which is the way we use to gauge the quality of the model. So we're going to call it cost function. And then there is an optimization part plus regularization. Now, these additional pieces, they introduce new parameters. So clearly one thing is the cost function. And this is the way by which we gauge the quality of the model which we have chosen. And a typical cost function, if we are dealing with a regression problem, so if we are thinking of regression, so we want to fit a continuous function in one way or the other. So the typical one, which you have encountered before, is the mean squared error. And the mean squared error is then typically given by 1 over n, and then it's the norm 2. And now I'm going to use a notation here where I use t for the targets. These are the outputs of, actually the values which we want to reproduce. So if we have a function with an input x, then this produces some final result t, and then we have minus here y, and now I'm writing these in as vectors. So this is the norm 2 squared. So let me quickly remind you of the norm 2 of a vector. So often people are a little bit sloppy, but this would now be given by the square root, and then I would have the sum over I, and then I have all the, sorry, x, let me just repeat that one in case you've forgotten, over all the elements, so it's xi squared. So this is the norm 2, and if you square it, this is just the elements of a vector. So this is a vector x over vector x just squared. So if you do a regression, the typical cost function would be the mean square error, where t is the target. These are the values we want to reproduce. And the y's here, these are the model outputs. And in our case, these are going to be the outputs of a neural network. So if you're dealing with a classification problem, if you have a binary classification problem, something like the cross entropy is a typical cost function which you want to optimize. So this is one type of problems which we have. If you look at this y, so let me just quickly specify that one. So this y is going to be a function of the unknown parameters, which I'm going to label with a common denominator theta, and x. So x are the input values. So x is the input to the network, or the input data. So typically, you could now have a function t, which is given by f, a given function, with x as an input, just to give you an example. And then we want to set up a model which produces y, which closely reproduces these targets t. So feel free to interrupt me if something is unclear here. Now, this theta, this is a common denominator for the parameters, or the unknown parameters of our model. And what we have now is a cost function. So if you look at this mean squared error, we are going to rewrite this cost function as a function which depends on these parameters theta. And our y, which is our model, depends on these parameters theta. So what we are going to do now is to find the optimal theta, which is written with an hat on top of it. So this is the optimal value, which optimizes, let's say, the mean square error, or any of the other cost functions which we have, which we use to gauge the quality of the data with. So this is going to be given by a optimization problem where we find the minimal argument. And then this theta is typically a member or a vector of a length m, or it could also be a matrix. But if we assume now that we have m such parameters, and then we're going to optimize this function here. So this is the basic setup which we have after we have defined a model. So we need a cost function. The cost function is meant to reproduce this target data, which are produced through some kind of function which we don't know, this function f of x, with an input variable x. An X can be a vector, it could be a matrix, it could be a more complicated object. Hopefully not. And we are coming back to these parameters theta. Now you can just think of these as this theta as a container for all the unknown parameters which we need to optimize. Now, when you say optimization, that means that we have under this second topic, cost function optimization and regularization, we have the optimization part. And here, I know that many of you have written a code for typical gradient descent method. So the most standard one and the simplest one is a gradient descent. So we have a gradient descent with momentum, and I'm going to use an acronym here, so I don't need to write GD, a gradient descent all the time. So I'm going to use an acronym GD here. So GD with momentum is a way to actually speed up the convergence of a gradient descent algorithm. These are iterative algorithms which try to find the gradient of the cost function and minimize the cost function so that the gradient is actually equal to 0. We have things like stochastic gradient descent, stochastic GD, which is then normally abbreviated to SGD. And here we have many variants. We have stochastic gradient descent with and without momentum. And then we have what we might call as schedulers for the learning rate. So algorithms within this basic, overarching container of gradient descent methods, we have ways by which we can update the learning rate, which becomes a parameter. And since everything we are doing is in a way an approximation to the standard Newton-Raphson way method for finding the roots of a function. In our case, this is to find the zeros of the gradient of the cost function. So we need some algorithms for the learning rate. And these are algorithms which in a way try to mimic the fact that when we set up Newton-Raphson's method, we actually not calculating the second derivative, and which is defined by a matrix called the Hessian matrix. We don't want to calculate that one, so we have algorithms for the learning rate. And these algorithms are typically adaptive learning rate algorithms. There's one which is called adaptive gradient. And we are coming back to these things when we are looking at the codes next week. And then we have the root mean square propagation, RMS prop. We have another method which is very popular, which is adaptive method with momentum, etc. And as I've been telling to many of you, this is actually one of the really delicate parts of a machine learning algorithm, that is finding the gradients and then optimizing the gradients and the parameters which are linked with the gradients. And clearly, if you can make an improvement to any of these existing methods, as I've been jokingly telling people, you will get many, many more friends. And I'm not inferring that you don't have friends, but these will be friends who will cite you. Just to mention Adam, which came in 2014, that has more than 100,000 citations already, which is a pretty impressive amount of citations. So the optimization part is actually the delicate part of any type of neural network or deep learning or machine learning method. Then finally, we have regularization. So that allows us to put some constraints on the optimal parameters which we have. And the typical regularization terms are an L1, where we would have a parameter lambda, which is then multiplied with the norm 1 of the unknown parameters. We have a so-called L2 term, which we can add, which is then given by a norm 2 of these vectors. We can also make a mix of L1 and L2 regularization terms, and this is often called elastic net. So there are many types of regularizations term which can be added. And then we have lots of other types of things which come in addition. And one of the problems when we're dealing with neural networks is something which is called exploding gradients or vanishing gradients. And there are techniques to deal with that. There are further techniques to reduce the complexity of a neural network. And we will come back to that. Any questions so far? So these are some of the basic elements. Now, there's one thing which I also wanted to remind you of, and that's called the universal approximation theorem. So let's just bring this up here, universal Approx theorem. And that's a central theorem for all neural networks. And that simply states, and the original one was actually a tour de force real analysis to prove the convergence criteria for neural network with at least one hidden layer. And this is after Sybenko, or Sybenko, I don't know how you pronounce it properly. So this was back in 1989. And that simply states that let sigma be any continuous sigmoidal type of activation function, or just function, be any continuous. This was later extended by Hornick in 91. Be any continuous sigmoidal. And I'm going to remind you what the sigmoidal functions are. Function. And it has the property that this sigma of z, so z is the argument, that goes to the following limits, goes to 1 as z goes to infinity, and it goes to 0 as z goes to minus infinity. So one function, one example, and I also wanted to say that I'm gonna use this sigma to indicate the activation functions in a neural network. So a typical one is the sigmoid function. This is just an example. And that is given by 1 divided by 1 plus e to minus z here. And if you plot that function as a function of z, the argument, you will then see that this function here, when c goes to minus infinity, this goes actually to 0. So we can put 0 here, and then we have 1 here. And you see now that when z goes to minus infinity, then the exponent e to the minus e goes to 0. So we have just 1. So that means that, and this is very schematic, the function looks like this, and then it goes up. So this was not the best drawing, and you can see what kind of skills I never developed properly here. It should actually be closer to 0. So let me just try to redraw it here. So this should be something like this, and it raises, and then it goes to 1 here. Now, so then, if you have then given a function, so let this be, the sigma be any continuous sigmoidal function, then given a function f, which is defined on what's normally called the unit cube, and these are complex numbers, 0 to 1 of dimension d, and a parameter epsilon, which is larger than 0, then there is a one hidden layer, network, that which we are going to describe with f, and then we have this input parameter x. So f is now the network itself, the model which we have, and this is defined in terms of the parameters of this hidden layer, which now are given by the weights and the so-called biases. So typically this theta is going to be a collective container for what we are going to call the weights, which link the inputs with the outputs, with the inputs to the layer, and then some bias, B. We don't need to specify these quantities yet. But the only thing we're saying now is that there is such a function, and this function is a function which now is so that we have f of x of these parameters theta minus this function f of x, which is describing our data, which is actually the function which we could have started with. And this is less than this specific error epsilon. And this applies for all x, which are element in the complex set of numbers on the unit cube. So any continuous function of this uppercase letter f of x, which is supported on the unit cube, can then be approximated by a one-layer sigmoidal network to arbitrary accuracy. So with sigmoidal, it means that the activation functions have this specific behavior, which you see here. And if you were to take a function like the tan hyperbolicus, this will also be a function which fulfills that condition. So that means that I can actually approximate any function, any continuous function, uppercase letter f, with my neural network, which consists with at least one hidden layer. Now, Hornig in 91 extended the theorem by letting any non-constant bounded activation function to be included. So in 91, we had Hornig extended this theorem, the theorem to apply to any. So remember that the sigmoid function or the sigmoidal functions, they are bounded. Extended the theorem by letting any non-constant bounded activation function to be included. So none of these proofs do actually give you any insight into the relation between the number of nodes or units which you have in a hidden layer and the error estimate epsilon, nor does it give you any hint about the number of hidden layers. So this means that these are things which we have to play with as parameters in our model. So the thing which we have is a theorem which states that we can approximate a given function to a specific precision with at least one hidden layer. But we cannot say anything if we go back to the basic definition of the model, which we have up here. We cannot say anything about the connection between hidden layers, the number of nodes on the final result epsilon. So this is something which we typically would play with. So we would start making a model which has just one hidden layer and a given number of nodes. And then we could compute, let's say, the mean squared error, if that's the gauge which measures the quality of the model. We would then continue, we would add a new layer, or we could just add more nodes in a given hidden layer. And we could continue then till we find the best possible representation of the data set which we have.
Morten?
So, yep.
Can I ask just,
yep.
when you say a bounded activation function, what kind of function is that?
So
is that,
if you look
is it like that just any boundary? Okay.
Yeah. So bounded here would typically be that if you take sigma z here, you see that it goes to 1 when this goes to 0. So that would be a bounded function. And then similarly, you have here would also be a bounded function. And what he did was actually by letting any non-constant bounded activation function to be included. So something like the ELO function, the exponential leaky unit, is a typical example of that. And there are tons of these activation functions. And
but isn't leaky. Is that unbounded, isn't it?
That is actually unbounded, and people have been using that. So what you will see now is that people have been extending this to other types of functions, because what they have seen in their data sets is that for specific data sets where you don't have this problem, where you typically reach a maximum value for Z, then you can use it. And keep in mind also that the quantity which is often more interesting is actually the derivative of it, which you plug in the training of your data. You need also the function value, but in case your Z doesn't explode here and you don't reach this specific limit, then clearly also the ReLO function will have a maximum value, which will, because the ReLO function is defined by your input argument multiplied with a constant. So you can then hope that it doesn't explode. But that depends clearly on your data set. So you have to be a little bit careful when you use this ReLO function. But the original theorems, they apply to that. It also means that it does not mean that the neural network can be fitted, used to exactly compute any type of function. What we get is actually an approximation that is as good as we want it. So you have to keep this kind of constraints in mind when you apply all these type of machine learning methods. And the class of functions that you can approximate in the theorems, they are limited by the continuous ones. So if your function f of x is discontinuous, it won't in general be possible to approximate it. However, a neural network may actually still give a decent approximation, even if we fail in some points. So that leaves a lot of practicing and trial and error for the users. So in principle, it's the theorems state that this applies to continuous functions, where the continuous function is this function f of x, which we want to reproduce. So there are some mathematical limits on what a neural network actually can do, but then people actually tend to use it in many other contexts or different contexts, where in principle, the universal approximation theorem should not be applicable. And this is clearly also the case when you have discontinuous functions. And you will also see statements in scientific articles where people just used one type of activation function, and then they would simply say, even if this activation function perhaps is not the best one for that model, this is the one which works best for our data, and we don't know why. So the whole field of the mathematics of deep learning is a field which is, how to say, is a pretty new field, and it's growing, and there's a lot of mathematical interest in exploring more the what you might call the mathematics of deep learning. So what I want to do now is actually to set up the kind of machinery which we need in order to write our own code for a neural network. And next week, I wanted to bring these things up, and then we are going to move over to convolutional neural networks the week thereafter. And the kind of idea for the first project is that we try to, as best as we can, to see if we can write our own code for a convolutional neural network, or eventually a recurrent neural network. But let's now go back to a drawing of a neural network. So let's now put this up as the NN. I just call that the structure of the NN. And the structure of a neural network is now a network which contains an input layer, where I'm just going to write this as X, and it can contain many nodes. If you're, for instance, if you want to recognize images, then typically what you would feed in for an image would be the pixels. So if you have an image with 20 by 20 pixels and just one color, that would give you 400 input nodes. So this would be what we call the input layer. This information is now fed in to the first hidden layer. And I'm going to write this first hidden layer as a box here. And we are going to put the label 1 here. So this is the first hidden layer. The input is connected with the different nodes in this specific hidden layer with the weights. And I'm going to put a label 1 here to indicate that this is what links the input layer with the first hidden layer. In addition, what we have is a parameter B1, which are the so-called biases, which are often used in order to hinder that the training of the network stops because the weights are 0. So that means that we would have a container here, theta 1, which is now going to include these weights. Sorry, I use a subscript here, and I should stay with the subscripts. So let me just rewrite it, and then we can take a small break. So B1 and B1 here. So these inputs, they are then given in terms of a function z. So we call this z1. And this z1 goes into the activation function. And now I'm going to write this in terms of, I don't know why I put the superscripts instead of the subscripts, because I have subscripts in my notes, but my hand wants to put a superscript. So I'm having a activation function for every specific node. And I'm going to simply write this now as an activation function sigma 1 of z1. And that produces an output. And this output is something which I will call for A1. These are now vectors or matrices. So this output is now fed into the next hidden layer. So which is layer 2 here. There is a weight function, W2. We have a container here for the weights and the biases, W2 and B2. So we have the biases here, B2. This produces a new function or value, sec2 here, which then goes into the activation function, Z2 of sigma 2 of Z2. That produces a new output, A2. And this continues now all the way to the final layer. But I see that I'm running a little bit over time. So I would suggest that we take a small break and then we continue with this. And then we are going to remind ourselves of the backpropagation algorithm and how we would calculate these derivatives using automatic differentiation. So that would be an element which perhaps some of you have forgotten or which you haven't studied so much, but which is simply essential when we are dealing with deep learning methods. So let me, so welcome back. And I wanted just to set up this schematic version of a neural network. So what we would have an input layer, and then we can have a given set of hidden layers and a generic hidden layer, which we could have here would be something like this. So we have a layer which we label with a lowercase letter L. This has a parameter set, theta of L, which now contains weights and biases, B of L. These weights are fed in here. There is an input from a layer L-1. This is the input from all the nodes. And I write this as a vector. I don't specify which node it is. This produces an input to the new layer, which is this Z of L. This is fed into the activation function of Z of L here. This produces an output, A of L. And this continues now till the final layer. So let's just write the final layer with an uppercase L. This has a set of parameters theta L. And I guess I don't need to repeat that theta L contains all the parameters. And this produces an output. And I'm just going to write that one as an A of L here. And this is the same as our Y. So Y, as we label it, is now the output of the last layer, which we call the output layer. So this layer, which you have here, is normally called the output layer. And here we compare this variable, through the cost function with the targets which we have, T. So this is a typical structure of a feed-forward neural network. We have some data which we feed in, and then we get this non-linearity due to all the hidden layers in the activation functions, which can allow us to reproduce a continuous complex function, which is normally not a linear function. In case we have a linear function, we should rather use standard linear regression, or we could just run a neural network with just no hidden layer, just an input layer, which goes through the activation functions with some weights, and then it outputs a value which is compared with the target. So when we now are setting up the parameters, what we want now is obviously to find the optimal parameters theta, which now contain the parameters for all the hidden layers and the output layer. So this is obviously going to be given by argmin of all the values of theta which we have as a function of this cost function. And in order to compute that, we need to define a cost function. So suppose now that we define as a cost function just a mean squared error. So that means that we take a cost function, and I'm going to simplify it, and I write this factor over half, and you will see quickly why we have this factor over half. And then I'm going to have a t here minus, and what I'm calculating is actually the norm 2 squared of these vectors. And this is going to be given by the output of x of theta. So this is given by the inputs and all the unknown parameters, x and theta squared. And we would typically rewrite this as a half of t minus y of x as a function of theta squared. So in order to gain some kind of confidence with what is going to happen now, because the feed-forward pass can be done and give a reasonable result if we know the optimal weights and biases or the parameters. But we actually don't know these parameters. And that is why we have to perform the optimization. The standard optimization is done by an algorithm which is called the back propagation algorithm. And that's the basic algorithm which is used in order to train a neural network. So let me just state that one. So the back propagation, and we are going to look at the simpler case now. And then when we have the simpler case, we're going to remind ourselves of the basic equations which we need to program. And then we're going to link this with a very, very important algorithm, which is called automatic differentiation. And I will try to link back propagation with automatic differentiation, because at the end, we are going to use automatic differentiation to calculate the derivatives in a neural network. And the derivatives are needed in order to update the parameters, or rather the gradients. So the back propagation algorithm, that is the algorithm which allows us to find the optimal values for the parameters. So what we would do then is to calculate the cost function. So we take the derivative of dc of theta for the final parameters theta of L, because these parameters define the value of y, which we want to compare with the targets. And this is the quantity which we want to drive to 0. However, this quantity here depends on all the previous parameters. So if you think of the cost function here, we should now be, I don't know why, I tend to put this subscript as a superscript. So here, I should now write theta of L here, because this is the output, and the output sees these parameters theta of L, which, however, depend on all the previous ones. So this is the object which we want to calculate. And if you now look at the derivative of this specific cost function, which here was set to the mean squared error, and you will often see that because the mean squared error is easy to interpret. It's also easy to make demonstration with, and its derivative is very simple. So if you take the derivative of that function, you see now that if we just use a standard chain rule, we will have a minus, and we get rid of the factor of 2. That's why you often will see the mean squared error defined with 1/2. So this is just for simplicity. So we get t minus y of x of theta of L. And then we have the derivative of dy of d theta of L, which I'm going to rewrite in terms of this generic output from each layer. So I'm going to rewrite this in terms of AL of x of theta L, and this is a derivative of dAL of d theta L. Now, the backpropagation algorithm is nothing but you applying the chain rule to calculate the derivatives of the previous values layer by layer. So let's see a simple example in order to gain some intuition about the backpropagation algorithm. So in this case, we have no vectors, no matrices, we just have scalars. So that means that we have an input x here, and this feeds in to a hidden layer, and there is an activation function. So we have a weight W1. This is an unknown parameter. X is just the input, and there is an activation function here, which I'm going to call sigma 1, which takes in x and has W1 as parameter. This is the only parameter I have. Now this produces this quantity. So this is the function. It produces a function A1. And this now is fed in to the output layer. So this is the hidden. And here we have a new activation function of x, and that depends on a parameter omega 2, the W2. And this produces now our final output, which I'm just going to label for y here, or we can actually write it as an A2 here, just to be consistent with what we had. And here we have the cost function, and this receives the target which we want to reproduce. So what we have then is that A1 is now equal to this function sigma 1 of x of W1. And if I look at the next function, this y, which is the output, which is equal to A2, is equal to the sigma 2 of x of W2 here. No, rather not x, but it receives A1. I was a little bit in a rush here. It receives this as input. And this is something which we then can rewrite as this function sigma 2, the function of sigma 1, and then you see the nested properties of these neural networks, and then as a function of W2 here. So that's the output, A2 or Y, which we now want to compare with the targets. So in our case, we have a cost function, which is again given by 1/2 of t minus y squared, which is the same as 1/2 of t minus A2 squared. And what we will need now, since we want to find the gradients, we need then dc with respect to W1, but we need also dc with respect to W2 here. So the backpropagation algorithm, which we are going to state a little bit later, is an algorithm which gives you the expressions for these derivatives. Now, in this simple example which we have, we can actually calculate these functions here. And one of the things we want to, if you look at these derivatives, when we take the last values here, we actually, what we want is that this dc of dw2 here is equal to 0. So we want to, this is the kind of function which we want to, or this kind of derivative which we want to drive to 0. Okay, so what we need now is to define an activation function. And we are going to make a simple linear activation function, which actually is not bounded, by the way. So let's just make a very simple model here. So we are going to have the first function, sigma 1 of x and w1, is going to simply be a linear function in w1. So that's going to be x times w1. Okay, and then I do the same thing with this next function, this sigma 2 here, which is x. Actually, it has a1. So this is equal to a1. It receives a1 as an argument, and it has a parameter w2. So this is the same as a1 multiplied with w2. And if we now look at what we have here, this is the same as, and if we just put it in here, this is w2 multiplied with sigma 1 of x of w1. And this quantity here is again the same as this output value y, which we also call for a2 here. So I hope there are not too many names here, too much confusion here. So if I go back now and I calculate this dc of dw1 here, then when I plug in the results, I get minus t minus y, and then I get a dy dA1, and then I have a dA1 of dW1. So that's the result for that one. And then I have the final one, which is dC dW2 here, which again is given by the derivative of the cost function. And then I have a dy y of dW2, which we can also rewrite in terms of this function y here. A dA2 of dW2 here. So these are the derivatives. And if I plug in these specific expressions, which I have, these specific cost functions, no, sorry, activation functions, which I have here. So this should be W1. If I take these activation functions and calculate their derivatives, you see now that I need the derivative of this function dy dA1. So this function here. And this function is now, I've just used the chain rule here. So I need the derivative of that one with respect to a1. And we know that this y is equal to a2 here. And it contains w2 now, but multiplied with x and multiplied with w1. So I'm just putting in the values here. And then I can calculate this derivative. And then I can calculate this derivative here. And when I do that, what I'm getting now is the following. So I have a very simple model. So if you're going to set up your first neural network, it can actually be useful to simply play around with this simple model here. So this is the same as minus t minus y times x times w2. And then, so this should be equal to 1 here. And then if I take dc dw2 here, that simplifies to t minus y multiplied with w1 times x. So these are derivatives which now we want to drive to 0. And typically what we end up doing now is to have an equation for an iterative equation using a gradient descent method to drive these gradients to 0. So we would have a w1 after iteration k plus 1, which is now given by w1 in the previous iteration. We have a learning rate, eta, which becomes a parameter. So you may remember that from when you wrote your first neural network code. And this contains now the derivative of this specific function, the dc of dw1. And then I have my w2 here of iteration k plus 1. And that contains w2 at iteration k minus eta of dc of dw2 here. And we have to keep in mind that w2 in this case is equal to W2 for iteration k, and that applies here as well. W1 is equal to W1 at iteration k. And then the only thing which remains for us now, if we want to do the training of this network, is actually to do this back and forth propagation. So we would now start the neural network here with a specific values for W1 and W2. We would produce a feed forward pass, and then we obtain a value for Y here. With that, we now calculate the derivatives and update the parameters W1 and W2. Then we have new parameters for W1 and W2. So this is the back propagation step, and we perform that one so that we move back with these derivatives and get a new value for W1. We get a new value for W2, and then we perform a new feed forward stage till we have a new output, which we compare with the targets we want to reproduce. And the final aim is actually to drive the derivative of this function at the last output node, which will be this one. And we want to drive that specific quantity to 0. Or rather, we can drive this quantity here to be as small as we want. So if this quantity stabilizes with this feed forward and back propagation stage, so every time we do a feed forward pass and a training of the parameters, and we get new parameters in the back propagation stage, then we have one iteration. We move forward again and then back again. That's the next iteration. And this way we will just continue till this quantity here doesn't change more than a specific amount, which we have defined. So in this specific case, we have very simple expression for the derivatives. But what I wanted you to pay attention to is actually the fact that when I look at this one, this depends now on derivatives here, which contain derivatives which I have obtained via the chain rule. So for the last one, it's pretty easy because I just have the derivative y with respect to the last parameter. But when I look at the derivative in the previous node, then what I need to do then is to apply the chain rule. So in principle, when you're setting up such a neural network, what you end up with is the following. So you would end up with, when you now, the first step you do is to calculate the derivative of the cost function with respect to the parameters. And now I'm not specifying the equations for the weights and the biases. I'm just leaving this as a generic quantity. So in this case, what I need now is the following. So we know that this is the derivative of d theta. And then I have the cost function, which depends, C depends now on the target values, and it depends on the output from the last layer, AL of theta L, and then obviously the X value. So when I calculate the derivative, depending on what type of function I have, if C is equal to the mean squared error, which we now put equal to 1/2, and I write it in vectorized form like A minus L squared, then what we get is that this dc d theta L is equal to the derivative of the cost function, and then we get a minus, and then we have a t here, minus AL. But then the next term which we have is a dAL or d theta L, without us now specifying what these A's are and what these theta L's are. So this is just a generic expression for the derivative at the last step. The next thing we do now is simply to use the chain rule in a repeated way. So if I now want to have the derivative of the dc of theta of L minus 1, the previous layer, that is obviously going now to contain the derivative with respect to the activations functions which we have, the type of mean of cost function which we have, etc., etc. And what we are going to get then is a series of relations which we are going to be given by dc dA of L of dA of L of d theta of L minus 1. We are going to continue this with a dc d theta of L minus 2, which is now going to be given by a dc dA of L multiplied with a dA of L, and then I'm going to have a dA of L minus 1 multiplied with a dA L minus 1, and then I have a d theta of L minus 2. And this is going to continue till we have reached the final layer. So that means that we are going to see something like a dc d theta of L, which is simply going to be given by a dc dA of L of dA of L, dA of L minus 1, dA of L minus 1, and then I have a dL minus 2, and this continues all the way till I have a last one, dA of L plus 2, dA of L plus 1, and then I have a dA of L plus 1, and then I have a d theta of L here. So what the backpropagation algorithm is just a repeated application of the chain rule, nothing more than that. So what I haven't done here is to specify what these different derivatives are. So if you look at this quantity here, or this quantity, and so on, we haven't specified them yet. Then we have really to look into the specific activation function which we have. We have to look at the way we set up the inputs to the activation functions in terms of the weights and the biases. And that's where we need to plug in our model. But the backpropagation algorithm, as you see it here from the simple example, which we put up here, you see now that the term before is actually given in terms of the derivative of the cost function, which we have here. And then we have the parameters. So if you look at this expression here, this expression is now the derivative of the cost function with respect to, if you go down here, you see I have the derivative of the cost function at the last value, the output value, which in our case, when we go back again here, is given by this quantity. And then I've been using the chain rule, and I can set up the derivatives of the value, the output value from the hidden layer with respect to these parameters here. And that defines the parameter dCW delta, the derivative with respect to W1. This is nothing but just an application of the chain rule. I could have specialized this one and added a, if we want to make the link with the equations which I put below here, what I could have done now is to rewrite this one in terms of a dC dA2 here, which is y, and then I have a dA2 dA1, and then I have a dA1 and dW1 here. And that would be the same as if we scroll down here, and you now look at this specific quantity which we have here. That would be something like this quantity which you see here. Or alternatively, the quantity which you see here, and so on. So the simple example hopefully gives you some intuition about what is going on here. So the backpropagation is the algorithm which we typically use in order to compute these gradients, which we have here, these ones. And these gradients are then plugged into the equation for updating the gradients in an iterative way. So typically you would run a specific number of iterations. And when you train a neural network, you don't want these gradients to vanish. And the reason for that is that if the gradients vanish, the training would stop. So it's not exactly the same as what you're doing in a standard regression problem where you drive the gradients to exactly 0. But what we are going to do then is to have a measure where we decide when we want to stop by looking at the value of, let's say, the cost function. And in our case, we want to minimize this and we want it to be as small as possible. And when it stabilizes, then we will claim a kind of victory. Now, there is if you look at these expressions here, we are just going back when it comes to derivatives. This process which you see, which we have set up here, without specifying the explicit expressions for these, which we will do next week when we are setting up the code, is something which we can link directly to the algorithm of automatic differentiation. So let's put that up. So this is automatic differentiation. And this algorithm is something which you would typically have in Python. This is given by a package which is called autograd. So you would have import autograd, automatic differentiation. Nowadays, you replace this one with JAX. And these are things which we're going to discuss a little bit more in detail when we come to the actual implementations here. So let's say a little bit about automatic differentiation. And automatic differentiation is one of these extremely popular algorithms, which now allows us to calculate derivatives to numerical precision. So the thing, as you've seen now, we need to calculate these quantities. When your cost function and activation functions, etc., become complicated, it's sometimes a little bit an irritation if you have to, every time you pop up with a new activation function and a new cost function, you're going to plug in new expressions for the analytical derivatives. It's much better to actually let the autograd or automatic differentiation to take care of the calculation of the derivatives. There are several reasons for that. So you can obviously set in the analytical expression of a function, or you can use libraries like Mathematica, or you can use symbolic Python to let them find an analytical expression for these quantities here. One of the problems then is that when you do that, is that these libraries, they often give you an expression which isn't simplified for numerical calculations. It means that even if you have an analytical expression for the derivative and for the cost function, etc., it may not be an equation which is easily translated into efficient code. So let me give you an example before we look at the explicit setup of automatic differentiation. So we are going to look at a function here, which I'm going to define. So let's just put up this example, and some of you may have seen this before. So suppose now we have a function which is f of x, which is equal to x squared plus the exponential of x squared. Its derivative, and we are going to look at the way by which we can encode this in an efficient way. So the derivative of that specific function is simply given by x of 1 plus x exponential squared argument, and then I have a square root of 1 of x squared plus the exponential of x squared. So that's a derivative. So in this case, it's a pretty simple function. Now, if you look at, suppose a library like Mathematica, or you use symbolic Python, they will easily generate these expressions. And you have a functionality like in symbolic Python, where you can ask symbolic Python to translate this this expression into a Python program or a C++ program or Fortran program as examples. However, when you take this expression here, this expression is not the most efficient way we can code the expression. Now, there are several reasons for this. So one thing you can do now is to calculate, if you now do a brute force calculation. So f of x in a brute force way without thinking is now to calculate x squared, so which is x times x. And now we are going to make an assumption in order to simplify the problem here. We are going to deal with floating point operations. So floating point operations are additions, subtractions, multiplications, divisions, and other mathematical operations. And I'm going to assume that an addition takes the same amount of time as calculating the exponential, which is not true. But let's assume that and define a floating point operation as just one of these operations. So this will be one floating point operation, which we are doing. It's actually not true when we do multiplication, but let's assume that for simplicity. Then I have the exponential of x squared. And if I don't think, then the exponential contains now x times x. So I'm not thinking, x times x, so that's one floating point operation. And then I have the exponential itself. So this is two floating point operations, two flops. Then I have an addition, x squared plus exp x squared. So that's another floating point operation, one flop. And finally, I have the square root. So if I do this without thinking, in total, I have 5 floating point operations. However, in this case, you would obviously say that, hey, I could now define a new variable, a, which is the same as x squared. I calculate a, and then I calculate exp of a. And that gives me obviously only, if I just have the argument here already pre-calculated, then I have reduced this. I'm going to reduce this to 4 floating point operations. So if I do that, then I would get 4 floating point operations. Now, one of the drawbacks with you using a symbolic package is that the symbolic package just takes this expression and just translates it into a code with x times x plus the exponential of x times x. And that's not very efficient from a computational point of view. Now, you can vectorize the code and you can use optimization options, where the compiler may identify that you are doing something unnecessary, that is to calculate x squared again and again. That's fully possible to use. But not all compilers are that smart. So this is the first thing. If you now look at the derivative, so if we also do the derivative without thinking, so let's take that one. And let's look at the numerator. So in the numerator, what we would have now is an addition, 1 plus the exponential, which is 2 floating point operation, x times x. So we have 3 floating point operations inside the parentheses, and then we multiply here. So the numerator has, without any kind of smart thinking, so the numerator has 4 floating point operations. So that is 4 flops. Next, if I look at the denominator, that's the same as the function itself, and that corresponds to 5 floating point operations, plus I have a division. So in total, if I don't do any smart thinking, nominator, so that is 5 flops, plus division, which is 1 flop. This gives us in total 10 floating point operations. So if I were to take symbolic Python and calculate the derivative, and then translate that derivative into a Python program, it would actually just translate it as it stands. Now, you could obviously say that I don't want to use a symbolic package. I actually want to use now a finite difference method. A finite difference method is a little bit, it's easy to implement. So you could now say that, okay, let me take my df dx, and I would approximate that one with a value of f at x plus a delta x minus f of x divided by this delta x. Now, this way to calculate the derivatives can easily become time-consuming. And the reason for why it can become time-consuming is that the function you want to optimize in machine learning and in deep learning methods in particular is a high-dimensional function. So that means that you would have to calculate derivatives in tons of directions. So if you have, it's not uncommon to have millions of weights. So that means that the function you want to optimize has 1 million of parameters. And clearly to calculate these derivatives means you need to calculate all these function values for all the iterations you do when you calculate the gradients. And that becomes time consuming. The other thing, which is a little bit risky, is that you need to define this delta x. And this delta x is a parameter which you clearly can drive to small values. But when you drive this to small values in order to get better and better derivatives, what happens then is that you can enter the region where you have round-off errors. And when you get round-off errors due to the representations of numbers in machine representation, then you can end up with loss of numerical precision. And then your derivative just goes wrong. And this is where automatic differentiation kicks in. And automatic differentiation makes actually life much, much easier for us. And it calculates derivatives to numerical precision by using the chain rule and appropriate simple functions like cosine, sines, exponentials, etc. So let's now look at this specific case with automatic differentiation here. And next week, when we begin with looking at codes, you will see how we can implement automatic differentiation to calculate these different gradients. And that's also going to give us, sometimes it may take a little bit more time in case you have an analytical expression, which is simple, but it gives you as a user much more flexibility because you can then switch between different activation functions, different cost functions, without going through the pain of finding the analytical derivatives. And in some cases, you may not be able to have analytical derivatives. So let's look at automatic differentiation with the same function. So we have this function, f of x, and this is given by x squared plus the exponential here. And we are going to set up the automatic differentiation using two ways of doing that. There are two modes, actually. One is called the forward mode. And I will explain to you what it means. And then there is another one, which is the reverse mode. And this reverse mode is also known as back propagation. And we're going to see that now. So let's look first at the forward mode. And what we're going to do now is just to define some intermediate steps. We are going to define a, which is equal to x squared. We are going to define b, which is equal to ex exponential of x squared, which is the same as the exponential of a. So we pre-calculate a. Then we are going to define a new intermediate step, which is a plus b. And finally, we have d, which is the square root of c, which is the same as the function f of x. So we have defined these 4 intermediate steps. And if you now look at this in a graphical way, so that we can link it with the way we've been thinking of a neural network, what you could think of now is that we have x as the input. Now x feeds in and produces this a, and where we have an operation where we simply square the variable x which enters. Now this has 2 branches now. One which produces the variable b, which is simply the exponential of this a. I just write it like that. And then this is simply added in here. So we put an addition sign here. So we have a plus b, which is c. So this produces c then. And then c goes into d. And here we have the square root, the operation. And finally, this produces the final variable f here. Now, what we could do now, when we want, because we want df dx. So df dx, and we're going to use the chain rule to calculate this. And we can do that in a feed-forward mode. So we would start with dA dx, which is the same as 2x, obviously. That shouldn't surprise you. And then we have dB dx, which is the same when we use the chain rule as dB dA of dA dx. Okay? So, and that gives us, when we plug it in, that gives us simply xp of x squared. I see that my time is running out here. So I'm going to wrap this up next week, when we then dive into the codes and going to look at codes for neural networks. And then I wanted to give you the first type of differential equations, which we are going to study using a neural network. And we are going to feed into the neural network the training from a differential equation solver. And we're going to see whether the neural network can learn how to solve this differential equation. And the differential equation is a pretty simple one, which we're going to set up next week. Next week, I will also use the first part to actually discuss the link between backpropagation and the reverse mode for automatic differentiation. And hopefully that will illustrate the benefits of using automatic differentiation, but also it will allow you to see the connection between automatic differentiation and what we did here. Because essentially what we're doing now is that we're using the backpropagation algorithm is simply an implementation of the chain rule in order to find the derivatives of all these coefficients and then getting the gradients. And then we can use an optimizer like Newton's method to find the final optimal parameters, which minimize, let's say, the cost function here. Okay, this is a little bit about the strategies for what is going to come. I'm going to switch off